C'est mon plaisir d'introduire aujourd'hui Gilles. Comment on dit Gilles en fait?
Pareil,
Paré,
pareil,
c'est ça. C'est comme un accent aigu finalement.
c'est ça, ouais.
Bon, tu vois. Gilles Paré qui est postdoc au CRM, postdoc boursier. Puis Luc Vinet, Yvan Saint-Aubin, moi-même sont ses hôtes. Euh, Gilles vient de terminer son doctorat à l'Université catholique de Louvain en Belgique, à l'Institut de recherche en mathématiques et physique. Et sa thèse portait sur, en anglais ici, Entanglement and Bipartite Fidelity in Low-Dimensional Quantum Many-Body Systems, supervisé par Christian Hagendorf. Donc, c'est ça. Et aujourd'hui, il va nous parler de choses dans la même lignée, mais avec d'autres collaborateurs, là, Pasquale Calabrese et Riccarda Bonsignori, sur une manière de découper l'intrication à l'aide de symétrie continue, donc le Symmetry-resolved Entanglement. Puis en plus, hors équilibre pour rendre la chose encore plus intéressante. Puis Gilles aime beaucoup le plein air et s'ennuie des bières belges. Donc, Gilles, tu as 50 minutes, là, grosso modo, plus 10 questions, mais c'est flou, là, et c'est des questions. Surtout John. John pose plein de questions. Là. Je ne sais pas si John est là. Là. Mais bref, environ 1 heure. Là, donc,
Oui, je suis là.
bon.
Mais je me
Environ
pose pas
jusqu'à
de questions.
4h35.
Ne t'inquiète pas.
Je ne suis pas inquiet, John.
Mais est-ce que c'est en français ou en anglais Il y a des anglophones, je pense, quand même.
Je suis en belge aujourd'hui.
En belge, ça.
Non, mais tu peux y aller en anglais là,
Ouais,
pour le plus grand auditoire. Puis on posera des questions en français pour diversifier la chose.
OK. All
So
right.
please, Gilles, you may proceed.
Okay, so thank you, William, for the nice introduction, and hello, everyone. Happy New Year. It's a real pleasure for me to be here and to give this talk. And for those of you which I haven't met yet, I really hope that we can meet in person soon enough. So as William said, today I will tell you about the project that we did with Riccarda and Pasquale at CISA during my thesis about this symmetry resolution out of equilibrium. So the plan for the talk is the following. So first I will give a brief introduction, and then I will tell you about the general context in which we study these quantities, which is the quench dynamics and the non-equilibrium system in one dimensions. And then I will move to the symmetry resolved entanglement measures and the actual results that we obtained in this context. And finally, if time allows, I will speak a bit about non-complementary subsystems in the end. So the keywords for this talk, well, it's entanglement, and this property was discovered in the early days of quantum mechanics by, in parallel, let's say, Schrödinger, but most importantly, Einstein, Podolsky, and Rosen in their famous now EPR paradox from 1935, which in a simplified version is the following. So imagine you have, say, 2 electrons that you prepare in a singlet state, so a combination of ups and down spins as written here. And then once you have prepared these 2 electrons in these states, you separate them and send them to distant observers, right? So for example, A, so typically Alice will receive the red electron and measure its spin. And if she sees that her electron has a spin up, then she knows that the state of the blue electron of Bob will be down, and conversely. So this apparent gain of information between these two distant observers is what we now call entanglement. So a definition could be that we say that 2 systems are entangled if performing a measurement on one influences the state of the other independently from the physical separation. And more mathematically, if we have two systems which are in states psi A, B, so state for the whole system A and B, then if the state can be written as a product of two individual states for the subsystems, then there is no entanglement. And if it's not the case, there is entanglement. So it's kind of a binary definition so far. So in our project, in this research, we do not study just two spins and two electrons, but we study entanglement in the context of quantum many-body systems. So typically what we have in mind is a system in 1 or 2 or maybe 3 dimensions, but which has a spatial extension and a bipartition. So now A and B are not just single electrons, but rather regions of space in which you have a large number of particles, or at least degrees of freedom, which interact and do possibly complicated things. So in this setting, the Hilbert space of the whole system is a product of local Hilbert spaces. And if your system is in a pure state, so if the whole system is described by one vector in this Hilbert space, the Schmidt's decomposition allows you to write this vector as a sum of product of individual vectors for the system A and B, with some weights here, which are the Schmidt's number or Schmidt's coefficient, which can be chosen to be positive. So this is very general. And so to describe your system, we use what we call the density matrix. So when the whole system is in a pure state, the density matrix rho is simply the projector onto this, this state. But if now you want to study the physics of system A only, then we introduce the reduced density matrix rho A, which is simply the trace over the degrees of freedom of B of the total density matrix. So these are like very common and standard elements when one studies quantum many-body systems. And for entanglement, now the question is, how far is psi from a product state? Because the definition I gave you before, it's just a binary one, right? It just is psi a product state, then no entanglement. And if it's not a product state, there is, but it's not quantitative. So now we try to make this question quantitative. And to do so, there are many ways to do to quantify this property, but the most, let's say, common and broadly studied ones are the so-called Rényi entropies and entanglement entropy, which are defined as follows. So the Rényi entropy is Sn. So here n is a number. It's usually an integer. It's this formula. So it's the logarithm of the trace of rho A to some power n. Right. And so in terms of the Schmidt number or coefficient pi, it's just a simple function here with the pi to some power n. And so when you take the limit n goes to 1 of this formula, you get a nice 0 over 0, right? Because the trace of rho A by definition is 1, so you get 0 over 0. But when you do the limit correctly, you recover maybe the most famous entanglement measure, which is the entanglement entropy, this trace of rho A log rho A. And so this quantity tells you how mixed the density matrix rho A is. So for example, if you have only one pi in the Schmidt decomposition, so you have a pure product state, then the entanglement entropy is 0, as it should be. And if you have more coefficients that are not 0, then this is a measure of the, let's say, the mixedness of this probability distribution. And for those of you who know about it, it's actually exactly the Shannon entropy of this pi. So there is a really nice connection between information, quantum entanglement, and also statistical mechanics. But I will not enter this today, but it's a really interesting point if you want to discuss later, maybe. Okay, so these are the measures that we will study, but now let's talk maybe a bit about the context in which we want to study them, because of course you can study quantum many-body systems in many different ways. You can study phase transition, critical phenomena, but in this case we study the non-equilibrium physics, so the quench dynamics.
Sorry, could I just slip in a question?
Yeah, of course.
In quantum mechanics, you can have a linear combination with arbitrary complex coefficients, but you've chosen real positive coefficients. What justifies that? What is the point of that? You've got square root of pi.
So I believe that you can always choose the basis phi a and phi b such that these numbers are real and positive. And we do this to have a better interpretation of the, at least as far as I'm concerned, of the formula here, which is, then you can see the pi, so the square of these numbers as probabilities, which then make up a probability distribution, and then you can study the entropy of this distribution. But
so are you saying that if I take an arbitrary complex linear combination according to some basis, that I can change the basis and turn those coefficients into real positive coefficients?
Yeah, so
the answer, John, is yes for a pure state. This is the Schmidt decomposition. It's not, if you don't, it's the singular decomposition. Because
singular value decomposition.
Singular value decomposition. So you need to look that up, but it's quite standard. Schmidt decomposition. For these states in particular.
Yeah, for pure state, of course. Yeah.
But who says that it's real positive?
It's a theorem. I mean, you can always have a basis phi a and phi b such that this is real. I mean, I don't know the proof now, but
you can absorb the phases.
Yeah,
in the way you define the Schmidt states phi IA, phi IB.
Yeah.
Uh-huh. I see.
Is that okay? Yeah.
Okay.
Okay. Right. So very good. So now let's forget for one moment about entanglement and just let's discuss a bit about this quench dynamics. And maybe the first question is, of course, what is a quantum quench? That's the point here. So it's a protocol which was introduced by Calabrese and Cardi to study the evolution and the isolated quantum systems out of equilibrium. And the fact that it's an isolated quantum system here, it's really important. So the protocol is as follows. You take a Hamiltonian, the one you prefer, okay, your favorite Hamiltonian, which depends on some parameter. So lambda can be a magnetic field and interaction strength, anisotropy, etc. And you prepare your system in the ground state of H for some value of the parameter lambda, say lambda naught. So you prepare the state in this system, and then you do the quench. You change lambda from lambda 0 to another value, lambda, and then you evolve your system with this new Hamiltonian. So your time-dependent state, it's just the unitary evolution of this psi naught. Of course, here, so the system is isolated, so the total system always remains in a pure state. So there is no dissipation whatsoever. It's always this unitary evolution. And then we can ask a few questions. So first, can we understand the dynamics of the system? Can we say anything meaningful about that? Can we characterize the steady states, and what is a steady state even in this context? And is it relevant to actual experiments? Of course, very, very good question. And to answer that, I need to introduce a few concepts in the context of thermalization in isolated quantum many-body systems. And if you're interested, there are actually excellent reviews by Pasquale on this topic, and excellent, I mean, scientifically, but also pedagogical, on the pedagogical level, right? So I think in 2020, these were like lecture notes from the Les Houches school. So it's really accessible and really interesting. So if you want, go check that out. So the first concept is the concept of stationary state, because as I said, the whole system is always in a pure state. So in this constantly evolving state, so the whole system never reaches a stationary state. So in this context, we say that the system reaches a stationary state if for any subsystem in the whole system, the following limit exists. So if the reduced density matrix for a subsystem reaches a stationary value. This is the definition in this context. And a second concept is the concept of thermal states. So maybe everybody knows this, but it won't be too long. So the thermal state is simply a state which is described by a density matrix, which is a thermal one. So where you have this exponential of the Hamiltonian divided by the temperature and the partition function. So the Gibbs ensemble, if you want, thermal matrix. And so combining these two concepts, we say that an isolated quantum system thermalizes after a quantum quench if for any subsystem the following equality holds. So there is a stationary state, rho A of infinity, and it is given by the thermal state, which is simply the trace over B of the thermal density matrix. And in this case, the temperature is fixed by the energy of the initial state. Because of course, again, since the whole system is isolated, there is no temperature. So it's really, the system A is like the system B here acts as a bath. And so the temperature is really an effective one, which depends on the initial states. And so there are some remarks. So as I said, the whole system does not thermalize because it's still in a pure state. It's only subsystems which do. And for integrable models, the story is a bit different. Integrable models never thermalize because, as you probably know, in the thermodynamic limit, there is infinitely many conserved charges. And so this constrains the evolution a lot. And instead, what you have is a generalized Gibbs ensemble. So the equivalent of the thermal matrix, now it's a generalization of this matrix, which contains all of the conserved charges and not only the Hamiltonian. So these are important remarks. So now in this context, let's go back to the entanglement evolution and what are we looking for, right? So in this context, what we usually study is we start from a low entangled initial state. So say a state which has zero entropy, entanglement. And throughout the time evolution, we monitor the entanglements of a system A. So we monitor S1 of T with time. So when the stationary state is known, so when we know the stationary value for the reduced density matrix, then of course you just plug it into the definition of the entanglement entropy and you get the stationary value for the entanglement entropy. And that's actually a very important point, is that in most cases, the stationary value of the entanglement is actually the statistical entropy of the relevant ensemble. So if rho A stationary is the thermal state, then you will the entanglement is simply in the end the entropy of a canonical ensemble and so forth. So there is really a connection between quantum mechanics, where you prepare your system, you let it evolve with the Schrödinger equation unitarily, and in the end, when you look at subsystems, you have statistical and ensembles which arise, and it's really interesting links between quantum mechanics and statistical mechanics. But of course, here I told you, okay, about the, let's say, the initial state, the final state, if we know it. So the question then is, what happens in between? How does the entropy start from being zero to being the statistical value, and etc.? How does it happen? Okay. And to answer that question, again, Calabrese and Cardi, but also Calabrese and Vincenzo Alba more recently introduced and studied what we call the quasi-particle picture for entanglement. So this is yeah, it's a way to produce a conjecture for the entanglement spreading in one-dimensional integrable systems, as represented in this picture. So you have an infinite line, and you take a subsystem A to be of length L. Say. So the idea is that in your quench, your initial state, psi naught, it is not the ground state of the Hamiltonian which generates the time evolution. Okay, otherwise, of course, the evolution is completely trivial. So it is actually a very high excited state of this Hamiltonian. And so you can see the initial state as a source of quasi-particle excitation, which will spread in the system with time. So the idea, but this is really, I mean, at the beginning, it's really not rigorous, it's just a guess, okay, a simple guess, is that at every point of the system, you have quasi-particles which are emitted in both directions, so with the same velocity, but in opposite direction. And the conjecture, the guess is that the entanglement is proportional to the number of pairs of quasi-particles which are shared between the system A and the rest of the system. Okay, so for example, the quasi-particles produced at this point in the system, after some time, one will be, okay, maybe here, one will be in system A, while the other one is in B. And at this moment, you have like 1 bit of entanglement, if you want, between A and B. So if you take this very simple idea, you can just do a counting exercise and get the general form for the entropy. So Sn of t. So, okay, so here the integral, it's just the integration over the different velocities for the quasi-particles. And Sn of k is, of course, let's say the crux of the calculation, because it's the proportionality constant, which is very hard to compute in interacting systems. But the general idea that you can see from this formula is that for early times, and v, of course, is the velocity of the quasi-particles, for early times, you get a linear growth proportional to t here. So, for example, at the very beginning, the quasi-particles emitted very close to the boundary will just very quickly produce entanglement. But after some time, the particle leaves the system A and never comes back again. So after some time, you have particle leaving and entering at the same rate. And so for large time, you get a saturation proportional to L, so to the size of the system. And this you can write as a simple integral over the minima of L and 2vt. This will come back quite a lot. So when you see this, it's very this behavior that happens. Right, so, okay, very nice. This is a picture, but now is it, one should test this idea, right? And so this was tested for the XY spin chain exactly by Fagotti Calabrese. So they made an exact computation and found exactly that the quasi-particle picture holds. So here you see the entropy as a function of time, and you clearly see the linear increase and then the slow saturation. But even in a more striking manner, actually, you can do this. I mean, you, maybe not me, but people did it in the lab, right? So Kaufman and collaborators in Harvard, I believe, actually managed to measure the entanglement spreading in time in optical lattices of ultra-cold atoms. And so here on the top right, you see this, I think they studied for 6 atoms. So here's the entropy between 1 atom and the rest, here 3 and 2. So you see this growth and saturation every time. But for the whole system, the entropy remains constant and almost 0, which basically tells you that the whole system remains in a pure state. So they managed to create a really isolated system and study the entropy evolution. So that's very, very nice, I think. So yeah, the quasi-particle picture in many cases seems to work. All right. Okay. All right. So now I defined what entanglement measures are. I told you about the quench dynamics and the context in which we want to study them. So now it's time to move on to the actual results and the symmetry-resolved entanglement measures. it's time to move to that. All right, so what is the idea? The idea is that you consider a system with a global conserved charge, okay, so Q, which splits as a sum over A and B. So typically in the simplest model that we actually studied, you could have a system which conserves the number of particles over time, and so Q would simply be the particle number operator. Okay, so you have such a system in a state rho which commutes with Q. So it means that you have a state for the whole system which is in a well-defined symmetry sector of the charge Q. Okay, so from this you can actually trace out the degrees of freedom of P, and what you get is that rho A, so the reduced density matrix for A, commutes with the charge in A. And this implies a block diagonal structure of the reduced density matrix. So here, the Q1 to QL are the values that QA can take, so the values of the charge in the system A. Sorry. And rho A is, and PQ are the probability of measuring this charge in the system A. Okay, so the sum of all the PQs gives 1. And they are such that you can define that the rest here is a matrix rho A that you call rho A of Q1, which is the reduced density matrix of a given symmetry sector. And with the PQ, which are normalization, then rho A also has trace 1, which is an important properties of reduced density matrices. So once you have this block diagonal decomposition, you can simply define the symmetry-resolved entropies as the previous entropies, but where you replace rho A by simply rho A of Q, where you choose the values of the charge. And I mean, that's it. I mean, of course, there is more to say, but the idea is simply that, is that you have a block diagonal structure in the reduced density matrix, and you take the reduced density matrices for each separate block, and you study the entropy in that case. Okay, so before I move on to some more technical details, let me tell you a bit about the state of the art of this business, let's say. So the original paper came out in 2014, where they studied the spin-resolved entropies in spin systems. But actually, it took a few more years for people to realize that it was actually a good idea and interesting. So the more recent paper that kind of launched the recent interest in this subject came actually independently and are by Xavier and collaborators and Goldstein and Sella. And one of their main initial result was the equipartition of entanglement. So that means that when you study the entanglement entropies of a given symmetry sector, basically and you do an asymptotic expansion of this quantity, actually the part that will depend on the charge sector, the part that depends on Q, actually vanish in the thermodynamic limit. So they are suppressed by powers of 1 over L, for example. So this is equipartition. It means that in the thermodynamic limit, roughly every symmetry sector contributes to the same amount to the entropy. This was the first result. And then there was an experimental motivation too, which I will discuss in the next slide actually shortly, but there is also an experimental motivation to study this. And so since then, there was a very big activity. So just, of course, it's not very, doesn't mean much, but just to show you that 2 years ago, or now 3 years ago, in the introduction of a paper on the subject, we really had a few papers, but now, I mean, it's really a fast growing field. There are really, really a lot of work done. So I know it's not the only metric to measure the interest of a subject, but I think it's important to say that it's a growing field. And now there are results in CFT in critical lattice models, topological systems and quantum Hall effect, integrable models and integrable field theories, 2D quantum systems, non-abelian symmetries, holography, so even people from high energy physics, disordered system, negativity, and in our case, non-equilibrium system. Okay, so there's a lot to say. Okay. Okay, so now let's just briefly mention this experimental motivation, which is actually by the same group as the other experimental result I showed you just before for the quasi-particle picture. So Luca and collaborators, they basically they understood that the total entropy S1 can be written as a sum of two different contributions when you sum over all the charge sectors. You have the first one, which is simply basically the entropy of the probabilities, so PQ log PQ. And the second one, which is a weighted sum of all the symmetry-resolved entropies, S1 of Q. So the first term is dubbed number entropy, and the second one configurational entropy. For the following reason is that basically the first term comes from configuration which do not have the same number of particles in each subsystem. Okay, so you got like this one blue particle in each subsystem, and then the two in only B, for example. So all of these different configuration creates this number entanglement, and the configurational one is the one that arises from the different configuration, but for the same number of particles in each subsystem. So 2 in A, 2 in B, but in different configurations. And in their experiment, so this is just a sketch, but they actually measure this in real physical systems. Actually, these two contributions have different properties. The number entropy starts growing and then saturates, whereas the configurational one waits a bit and then grows like forever. I mean, does not saturate soon enough. And so these experiments really show that actually to better understand the whole dynamics of the system, it's relevant and important to understand the symmetry resolution and these different contributions. So this was really a big motivation, at least I know for Pasquale, it was a big motivation to study this type of thing. All right, so now we have everything. We have the quantities, we have the context, we have the motivation, so it's time to make some calculation. So from the definition I gave you of these symmetry-resolved entanglement entropies, actually it requires to know the whole density matrix and then block diagonalize it, etc. So it really seems like a very non-trivial task. So luckily, Xavier and Goldstein and Sala, they propose a very elegant method to compute the symmetry-resolved measures. And the key ingredient is to introduce the so-called charge moments, this Zn of alpha, which is nothing but the trace of rho a to the n, and then you have the exponential of I alpha, and then this charge for A. Of course, if you put alpha to 0 and you put a logarithm here, you get basically the Rényi entropies. So it's really close and really close to the Rényi entropies, but yeah, a bit different. And so from these quantities, then you compute the Fourier transform, and you get the symmetry-resolved moments, Zn of Q now. It's simply the Fourier transform of this Zn alpha. And from these, you can compute the symmetry-resolved entropies as follows. So this was really, really important results that allowed many people, including us, to derive new results in that field. Okay, so once you have a new thing that you want to study, of course, the first thing you should do is to try with free fermions to see if you can extract any meaningful physics, and then see if you can do things that are more complicated, but it's always a good start to start from there. So we consider the model with U1 symmetry, which is simply the tight binding model or the XX spin chain. If you are more familiar with spin chain, this is just the XX spin chain with the Jordan-Wigner transformation. So these are fermionic operators. I'm assuming everyone saw this at some point, but if not, just ask me and I can tell you a bit more. But okay, this is a very simple model, and in that case, the conserved charge is simply, well, the fermionic number, which trivially splits as a sum over A and B. Okay. And in this case, so remember that our goal is to compute this Z and alpha. In this case, actually, Z and alpha has a very simple form. So it's this simple function where you have this exponential of I alpha, and then here CA is the 2-point correlation matrix. So if you can compute the 2-point correlation function in your model, in the free fermion model, then you can compute these charge moments. So if you are familiar with entanglement entropies in general, then if you put alpha to 0, you of course recognize the famous formula by Peschel. Yeah, right. Right. I mean, you recognize the usual way to compute the entropies from the correlation function, and so this works also for the charge moments. That was a nice result. So we applied this in the context of a quantum quench. So now our goal is to find initial states to do a quantum quench, which we will evolve with this free fermion Hamiltonian, and we will try to compute then this quantity as a function of time in this quench and see what happens. So to do so, we need to find the correct, not correct, but like suitable initial state, right? So we need to find an initial state psi naught, which is not an eigenstate of H. Otherwise, the evolution is trivial, as I already said. And such that the time-dependent correlation matrix is known, or at least that you can compute it, because that's the key ingredient to compute the charge moments, as I just said. You want it to be in a well-defined sector of the charge A, and you want it to be a low entangled initial state. State. So actually, such states exist. Okay, so for example, we considered the nail state and the dimer states. So the nail state is just the state where 1 out of 2 sides is filled with a fermion, or in terms of spin is just the product of ups and down spins. And the dimer state in 1D is just a product of singlet states over the chain. So rather simple states, but still we could extract some, I think, interesting physics. So now we have everything, so we can finally do the computation. And this is what we find. So what we obtain is that the log of Z and alpha, so the charge moment, has this very simple form. So you have an imaginary part, which is okay, what it is, but then you have this integral and this mean function, which, if you remember, is exactly the one which appeared in the quasi-particle integral for the entropies. So this is encouraging. And this function is a really simple function. So H, which depends on n alpha and x, is this probably not very surprising, but very simple function. Right. And so, okay, we tested this. So for the nail quench, it's this formula for x equals 0. So we computed, we compare this prediction with exact diagonalization of the correlation matrix, and it fits very well. And for the dimer quench, I mean, X is a bit more complicated. Now it depends on k. So, but the idea is really the same, and the results also match very well. And actually, so from these results, we can actually conjecture, because I told you, right, that this looks like the quasi-particle result. Actually, we use the quasi-particle picture and conjecture that in general, this log of Z and alpha will have this typical behavior. So an imaginary part, and then okay, the sum here is not really important. Could be a sum over different types of quasi-particles, but okay, whatever. But then an integral with some kernel and this minima function. Of course, in our case, this function is simply the function h, which I showed you, but in general, it could be more complicated. But at least we conjecture the general form for generic integrable models. All right. So now that we have the charge moments, if you remember in the steps, the charge moments, and then we have to compute the Fourier transform to obtain the symmetry-resolved entropies. So that's what we did. And we obtained the following results. So very similar forms for the nil and the dimer quench. So here, delta Q is simply the difference between the charge sector Q and L/2, which is the average value of the charge. So it just it's the charge sector, basically. And this J in the denominator here, actually this integral. So the kernel is not really important. What matters again is this quasi-particle behavior, which tells you that in the large time limits, this actually is proportional to L. This is important because then you see that what we have is actually equipartition broken at order delta Q square over L, because the first term here does not depend on Q, and the first term which depends on Q basically goes like delta Q square over L in the scaling limit. So that's our first result. And the second result, which is not obvious here, but I will show you a plot, is that actually the entropies starts to grow after a time delay, TD, which, I mean, the exact form is not important, but it depends on delta Q and it's proportional to it. That's a surprising result. And this is the type of plot that we obtain. So this is S as a function of T, right? And the different colors correspond to different values of delta Q. And you see that as delta Q increases as you go on the right, you need to wait some time before seeing that the entropy starts actually growing in a given symmetry sector. And yeah, this is T as a function of delta Q. So the dots are the numerical calculation and the line is the analytical prediction. So it matches pretty well. So this result was, to me, rather interesting because it's, I would say, counterintuitive, but also, I would be curious to see if this happens also in other models and in other contexts. So yeah, and this is for the nil, but for the dimer, we obtained the very same, got exactly with the same type of behavior. Okay, so before I move on to the case of disjoint interval, let me just tell you just a bit about the number entropy. Because if you remember, an original motivation also was this decomposition of the total entropy as the number entropy and then the configurational entropy. And so with all of our machinery, we are able to extract rather easily the number entropy. And we obtain this. So here, it's this J is this quasi-particle integral as before. And here are some plots. So what we have is that for small times, this J goes as T. And so you have a log T dependent. So you see it very clearly here. And then for larger times, it saturates to a value proportional to log L. And so in the large time limit, the number entropy has a negligible contribution to the total entropy, which goes like L. So you get an order log L over L, which of course goes to 0 in the scaling limit. So these are the two behaviors. And for the dimer, it's the same. And it was also observed in different contexts, which I will not discuss here, but it's something that is not very surprising, but still interesting to recover. Okay. All right. Good. So now I think I have like roughly 10 minutes. So I will discuss a little bit about non-complementary subsystems. Because everything.
Excuse me.
Yes.
I'm wondering, since the free fermion system that you consider has infinitely many other conserved charges,
right?
So does it change if you choose a different charge to look at this quantity?
Well, we haven't investigated that thus far. That's the first answer. Yeah, that would be interesting to look at. Actually, I don't really know how it would change. I don't know right now. We haven't looked at it so far. So that's my honest answer.
Okay, thank you.
Yeah, thanks. Okay, so everything I told you so far is about entanglement between a system and its complementary complements. Okay, so one line in a bigger line or things like that. But in some cases, we also consider systems where, say, system A, so in red, is made of two distinct parts, A1 and A2. Okay, but in this case, an important remark is that the Rényi entropies that we discussed a lot today, actually they quantify the entanglement between A and the complementary, but irrespective of the geometry. So here, even if A is made of two different parts, this Sn will not only quantify the entanglement between A and 2 together and the rest. Okay. So if you want to compute or to study the entanglement between A1 and A2, then you need to study other measures. So the first one is the mutual information, which is defined as follows. So you have a combination of entropies for A1, A2, and then the entropy for the whole system A. So this is the mutual information, but as a remark, it's not properly an entanglement measure because it can also have, it measures the correlation, but both quantum and classical between A and B. So it has very interesting features, but one should be aware that it's not completely an entanglement measure in the sense that people usually define it. Instead, one entanglement measure which actually is truly quantum is the so-called negativity, and in particular the logarithmic negativity, which has this very simple form. So here, rho A T1 is the partial transpose of the reduced density matrix, which is defined as follows. So you can write rho A, so the reduced density matrix, in a basis. Okay, so here, for example, the E1 and the E2 are basis states for the Hilbert spaces of A1 and A2. Right. So this is just writing the matrix in its spaces. And so taking the partial transpose just means that you interchange. So here you had I and K for the system one, and now you have K and I. So it's just transposing, but with respect to one subsystem. And the trace of the absolute value of rho A T1 is actually, it's very simple to see that this is related to the presence of negative eigenvalues in the spectrum of rho A partial transpose. So this is why it's called the negativity, but I will not enter into much details today. I think this could be also the subject of a whole complete talk. So just to mention this quantity. And so in the context of non-equilibrium physics, there is also a quasi-particle picture for disjoint intervals. Okay, so it's exactly the same as before. So you count the number of quasi-particles shared between A1 and A2. And if you do so, you realize that typically the behavior is as is shown on the left. So the time goes up. Okay, so you first have a delay. So because before having a particle share between A1 and A2, it has to be emitted from the center here. And so it takes some time before reaching the two subsystems. Okay, delay. And then you have a growth, a plateau, a decrease, and then it's zero all the way. This is what the quasi-particle picture gives you. And so for the mutual information, this gives you, so this is exactly the same kernel as the entropy as before, but now you don't have this simple minimum function, but you have a combination of maxima, which basically just reproduce this behavior I just told you. And interestingly, the logarithmic negativity, this is an important result from this paper, behaves as the mutual information with index 1/2 over 2. All right, so this is just the quasi-particle in this context picture. And so what we want to do is to compute symmetry-resolved quantities. So we introduce the symmetry-resolved mutual information as follows. So it's simply a sum with some coefficient here. And it's the sum over all the values of the charge for system A1. Okay, so we fix the charge in the whole system A to be Q. And so then we take the entropies of A1 with charge Q1. In A2, we have Q minus Q1, so that the sum is still Q. And then for the whole system, we have charge Q. And in this formula, the P here is the probability of having Q1 in A1, knowing that in A, we impose that we have the charge Q. So this is our definition. And we argue that it, similarly to the symmetry-resolved entropies, it also satisfies that the total mutual information can be obtained from the symmetry-resolved ones. This is not crucial now, but just to tell you, it has natural properties that one would expect. Okay, and so if you want to compute this quantity, well, we know now how to compute the symmetry-resolved entropies. So the only new thing to treat is this PQ. So to compute it, we introduce the doubly charged moment, which depends on alpha and beta, which is defined here. Okay, so it's really similar to the charge moments as before, but we now have two different quantities, alpha and beta, and QA1 and QA2. And then we take the Fourier transform and find the probability from this. Okay, so these are the new steps. So I will skip the details, but for free fermions, we find a way to compute it in a similar fashion as for the charge moments, even though the techniques do not apply directly. So we had to work a bit, but in the end, we could find a very simple way to compute the doubly charged moments. And we find this result. It's not important. The details is not important. It's just that you see we have different quasi-particle images. So here you have this minima of L1. Here the minima of L2. And then some function which depends on alpha and beta, but with this maxima, which are these quasi-particle picture for this joint interval. So these are like known pieces altogether. And this works really well. So to conclude, I will just show you then, from that we can compute the symmetry-resolved mutual information. And this is what we obtain. So we find the perfect equipartition for early times. Right? This was expected, okay? And for very large times. And for intermediate times, here, the equipartition is broken at order, the same order as for the entropy, so delta Q square over L. And it's similar for the nail and the dimer quenches. And finally, so I am a bit running out of time, but just in one slide, I will not say much, but for the negativity, if you want to study its symmetry resolution, actually you have to study its charge imbalance resolution. And this is because rho A of T1 commutes not with the total charge of system A, but with the imbalance, so with the difference between the charge in system A2 and the charge in system A1. So this is from a very nice paper here, but this is just, you just change the charge from which you do the symmetry resolution. And in the end, I skip you all the details, of course, but in the end, we obtain a very similar behavior as for the mutual information. So equipartition early times and large times, and broken in the middle. This is, I mean, it's not surprising that we have a similar behavior for the two quantities, but it's always a good check to recover these properties. All right. So now it has been 52 minutes, so it's time to conclude. So today I presented you some results regarding symmetry-resolved entropies, and we obtained exact results for the quench from the nail and the dimer states. And we find so equipartition broken at order delta Q square over L, a time delay, our results understood in terms of the quasi-particle picture, and we have an exact result for the number entropy. So this was for the entropies, and for the symmetry-resolved mutual information, we have exact results for free fermions, and in particular, we introduced a new quantity, which is this Z1 of alpha beta, which we could compute exactly. We also find this equipartition broken at some order, and our results are also in the form of a quasi-particle picture. So in the outlooks for these projects, of course, a very important issue would be to test the quasi-particle conjecture for generic integrable models, which is easier said than done, but still very interesting. One could also consider more generic initial states, because we studied, rather simple initial states. So one could study inhomogeneous states, for example. So the case of non-integrable models is also very interesting. So, for example, does the time delay holds in this case, or is it just a thing that holds for integrable models? Okay, experiments would be nice. I don't know how to do it, but if you do, feel free to go ahead. And yeah, the negativity, as I said, this is a work in progress, and it's very soon to be on the arXiv normally. And so, yeah, with this, I thank you, and I am here if you have any questions.
Merci, Gilles, for a nice talk. So it's now open to questions, especially the students have any questions to start. You can also type some question in the chat. And
excuse me, may I ask a question?
Yes, sure.
So I'm just wondering, in the end, you're mentioning about a homogeneous initial states, but with the homogeneous initial state, there might be some current with respect to the charge that you want to consider.
Yes.
Would that be a problem? Because right now you're considering quantum quench, which is homogeneous. So I guess the charge, the current just cancels, right? So
again, I guess your question are more like things we will look into in the future. So the thing is that these effects, we don't know how it would affect our result, and that's one of the reasons why it would be interesting. So we don't have any preliminary intuition or results in that respect. It's just a natural say things to look forward. So again, I'm really sorry, but it's the same answer as before, is that so far I don't know, but for sure it would be very interesting to investigate that. Yeah.
Okay, thank you.
I would have a question too.
Yes.
Do you have any intuition about the existence of something that would explain the existence of the delay you see in the growth of entropy, and why maybe its absence in the other graph you showed?
For the existence of a delay, so this is really a hand-wavy explanation, but one way maybe to see it is that, say, if you start from a state which is like as a spin up, 1/2 spin down, then with the quasi-particle picture, you somehow to reach to start to enter in a sector of a charge which is really far from, say, zero magnetization. You need to excite a lot of spins, so make a lot of spin flips. So if you start from a zero magnetization state, the time to excite a lot of spins to reach the magnetization free sector, for example, will take some time, and the quasi-particle propagate with a finite velocity. And so this is a hand-wavy way of understanding why the symmetry sector, which are further from the initial one, which is the delta Q equals 0, so the one where the charge is exactly the mean value, take more time to get activated.
Okay, it makes sense. Yeah. So, given you can interpret it with the quasi-particle excitation model, could you maybe like conjecture a form for the delay? Like you had this you could estimate the growth of entropy. Could you also have an idea of the delay?
In general, so that's a good question. I think we expect that the delay, at least for for small enough delta q's, will remain proportional to delta q. This is what we expect. But for larger delta q, somehow, I mean, I did not show you the full curve, right? But it's a line. But when you get to bigger delta q, actually the delay is no longer linear. So yeah, this is not something that we have, because we still haven't done the generic case. So in that case, it would be interesting to understand that. But you know, now I will just say that for small delay, it will be proportional. But then the general picture remains to be constructed, I guess.
Thank you.
We have more questions before I ask questions. Okay, go. I can ask a question then. Can you, c'est en français, on s'amuse. Est-ce que tu peux montrer les états initiaux? Encore, les initial states? J'ai malheureusement pas retenu entièrement. Pourquoi ces deux états spécifiques? Première question. Puis deuxième question, à quel point que je peux généraliser les états initiaux sans perdre trop en faisant ça, là, sans rendre le calcul trop complexe. Donc, vous avez, je présume, pensé un peu à une famille plus générale d'états initiaux. Est-ce que tu peux nous dire un peu là-dessus? Là, sur...
Ouais. Donc, la première réponse, c'est pourquoi ces états? C'est parce que ils sont assez simples, et donc du coup, leur matrice de corrélation, le C ici, était déjà connue en fait. Donc, quelque part, il y avait une part du travail qui était déjà connue, donc on a pu directement faire des calculs dans ces modèles, pour ces états initiaux. Alors, évidemment, donc ça c'est un des points que je dis, c'est que ce serait intéressant de regarder pour des états initiaux plus généraux. Mais je n'ai pas encore beaucoup d'intuition sur lesquels vont marcher ou pas. Donc, ce qu'il faut, c'est pouvoir être capable de calculer cette matrice de corrélation en fonction du temps. Donc, c'est des fermions libres, donc il y a beaucoup de techniques qui existent, mais il faut quand même s'assurer qu'on puisse le faire. Mais donc, oui, donc, par exemple, une famille d'états qui est intéressante, c'est ces états inhomogènes dont je parlais. Donc, ce serait par exemple de prendre un ground state, un état fondamental du système A1, enfin A et B, séparément, et puis de les coller et de prendre ça comme état initial, par exemple. Ça, ce serait un état initial très différent. Mais il y a aussi des papiers de Jean-Marie Stéphan, Jérôme Dubaï et Jacopo Vitti, où ils étudient ce genre de cas. Donc, dans ce cas, c'est aussi possible probablement de faire des calculs et de comprendre des choses. Et là, ce serait ce serait une physique différente, vu comme Johan l'a dit aussi, comme ce n'est pas homogène, il y aura l'image de quasi-particules sera modifiée à cause de certains courants, etc. Mais je n'ai pas une recette générale miracle, mais à mon avis, si c'est des produits raisonnables d'opérateurs de création et d'annihilation avec le théorème de Wick, on devrait être capable de faire des calculs.
C'est ça, dans ton cas ici, les états initiaux, comme tu le mentionnes d'ailleurs dans le dernier point, c'est qu'ils sont très faiblement intriqués. Là, le premier, il ne l'est pas d'ailleurs.
Ouais.
Donc, du point de vue qualitatif, est-ce qu'il y a des propriétés distinctes que tu tendrais à avoir pour des états qui sont intriqués plus fortement, là, comme un fondamental, là, par exemple?
Ouais. À mon avis, si on prenait des états intriqués, mais quelque part, en tout cas dans le cas de la dynamique, on peut étudier plein d'autres choses, mais pour la dynamique, c'est un peu comme si on partait de plus loin. Donc, à mon avis, juste que le point de départ ne sera pas S égale 0, mais ça risque, s'il y a toujours ces propriétés d'état homogène qu'on peut décrire avec des quasi-particules, ça risque d'être la même physique, mais quelque part juste shifté dans le temps. Mais bon, je dis ça, mais je ne l'ai jamais fait. Mais après, oui, par exemple, le cas des deux états fondamentaux, ça pourrait être intéressant parce que séparément, ils sont fortement intriqués, mais comme c'est un état produit, en tout, il n'y a pas d'intrication entre A et B, mais A et B sont tous les deux fortement intriqués. Donc peut-être que ça pourrait être intéressant. C'est vrai que le nez, il n'est pas intriqué, mais peu importe ce que tu prends comme système, il n'est jamais vraiment intriqué. Donc,
Okay. Ben, si je pose la deuxième question, si personne m'arrête, je vais aller rapidement. Ton info mutuelle résolue par charge que tu définis, maybe I'll go in English, I1 of Q doesn't seem to obey positivity. It's not necessarily positive, which is different from the usual mutual information, the global one, where you sum over all sectors. And that's, a nice property to have. And then you have even stronger properties on mutual information. So, can you comment on whether there are other choices that would be positive, or whether is this like some preferred definition, or is it a good one? Is there a better one? Or
yeah, so actually it's really good because all the question everyone asks today is basically just another research project, because as we say in the paper, so this definition at first glance looks reasonable. I mean, because we didn't really know how to define such a quantity, because each entropy has its own symmetry resolution. But indeed, as you said, it's not positive, and actually, if you look close enough here, it's not positive, right? But
that's how I saw it. Because
yeah,
the question, it wasn't obvious. I mean,
so a good observation.
Getting old. So, but the figure sold it. Yeah, you
so
see, it's negative.
So it's not a mistake in the sense, maybe the formula is not. Okay, but so what we argue is that this is probably not the best definition, and actually our paper was also an encouragement to other people to try to come up with other possible definitions, because since it's a combination of different quantities, there is not one obvious choice for this quantity. But we still thought that this definition had interesting properties, such as, well, for example, the fact that it can be used to reconstruct the total mutual information, the fact that its quench dynamics can be studied and actually resembles the quasi-particle dynamics that is known for, let's say, the total mutual information and so on. So it has interesting properties, but it would be actually really interesting to investigate further if one can fix this problem and argue, like to find another definition which would still have the nice properties but fix this problem. But this is totally transparent in the paper. We say, okay, it's a guess, and maybe not the best, but it would be interesting to look for other properties of this quantity and maybe better candidates for final symmetry-resolved mutual information.
But it still goes to 0 at late times.
Yeah, right. The fact that it's not positive, it actually does not change much. Right? It's really negligible. I mean, on the plot.
Is there the regime where it's negative? Do you understand when does this thing can be negative? Is that something that you have some more heuristic or physical understanding of? Because it seems, so this is for, can you remind me for which initial state are you doing this quench on this figure?
Actually, I think this was for the dimer, but it's really similar for the two.
So so this is for dimer, but if you do for the Néel initial state, you also get negative region?
I think it was almost the same.
But you're not sure. You're not sure, right? Or
yeah, I'm not sure because I haven't looked at this.
because I'd be curious, because I mean the dimer state has some entanglement though, but the other one is a product state, so I don't know if that is a factor.
Yeah, but this will take 10 seconds to check. Just right now, okay, but yeah, I mean, we understand why it's negative in the sense that in the formula we have, it's obvious which term causes the negative part, and it's actually not a leading term. So probably if we rescale it properly in the thermodynamic limits, this curve actually eventually goes to the straight line. But physically, we don't have.
So you're saying this is a finite size?
Yeah, it's
because I mean it's T over L, but L here is remind me which
it's
dimension?
It's the size of A1 and A2, so it's like the total size of A in 1D right now.
But I mean, yeah, it's not fair because it's scaling, right? You divide T over L, so if you take longer chain, but shorter times. So
yeah, but like if we take longer chains for the same value of T over L, this eventually gets back to 0. So that's what I mean in the sense that it's not a big deal. At least in this case, it was not like minus L, like like a very big negative, and thing. It was just a slight constant term, which is negligible compared to L in the scaling limits, but I mean, it's still there. But yeah,
so it's a constant term.
Yeah. So for the Néel, it's also negative, right?
So then you would have like this delay almost, right? If you forget about this being negative, it's very small. It's like 0. You have a delay before the.
Yeah, that's exactly the delay that we expect from the quasi-particle propagation that I explained. It's exactly this. I don't know, like D over V, or it has to do with the separation between the two subsystems. Right. If you put D equal to 0, it starts to grow immediately. It has to do with this. So this delay is really, we expected it.
Okay, good. So do we have other questions? I think it's late enough and we had plenty of questions. So merci Gilles pour la présentation, merci pour tes réponses. Merci à tout le monde. Thank you everyone, and see you next week for another seminar.